I'm Haris Antoniadis from the University of Oxford. In the second part of our podcast, we will deal with some more practical aspects of the experimental design in basic science. I have with me today Dr. Marialena Trivella, a senior medical statistician from the Center of Statistics in Medicine of the University of Oxford. Dr. Trivella has been supporting medical research for many years now, and she has been involved in many basic science research projects so far.
Thank you, Harry, for the introduction. I will be talking to you today about the principles and fundamentals in basic research in cardiology, taking into account the peculiarities of experimental models used in that area. To this extent, I'd like to highlight that this video isn't giving all the answers in research in cardiology, but it is merely a starting point of steps and procedures a researcher should bear in mind when considering a basic research project. If we're doing research with patients, we will very likely have different considerations and issues to deal with. Setting the right question is crucial to a project. Without a well-defined research objective, it is not possible to continue to design a project and analyze any data. So really everything rather depends on this. Our question should be accurate, well-defined and concise. The elements to consider when deciding the objectives are given by the well-known abbreviation PICO. And let's see what it stands for. P stands for the population we need to consider. But as we're talking here about basic science, we substitute this with experimental models, cells, animals, or whatever it is we're using. Then the I stands for intervention. In other words, what kind of treatment or intervention are we applying to our sample? The C stands for comparison. In other words, what groups are we going to compare? And finally, the O is the outcome, and it's perhaps the most important part. What outcome are we looking to measure and explore? So for our research stage to be complete, in addition to the question itself, we need to describe these factors. Only then we can talk about a fine-tuned question. Next stage is the design stage of the project. Ideally, all considerations here should be taking place before the analysis stage, and this is perhaps where a lot of researchers sometimes confuse the two. It sounds very difficult, but it is much simpler, actually, if you consider all these factors before you start any analysis. First of all, choosing the right sample comes under here and is very important. Then we have elements of randomization and blinding, randomization for the animals or the assessors. Then we decide on what information needs to be collected and an adequate method to collect these data. And finally, we need to decide on the statistical strategy for the analysis. We will look at all these points separately, but what we will do is take the last three items and consider them more naturally while we talk about the analytical methods further down the line. We just need to remember that describing these methods actually belongs to the design stage of the study. So let's start with the sample size. When reading a journal article, the first question we ask is, how good is the estimate presented? Could the observed differences be due to chance alone? Or is there really a difference between the groups? This is where sample size plays a key role. Larger studies offer better precision, and consequently we have a better probability to detect an effect, if that effect really exists. We call that probability of detection power. In reality, what happens, unfortunately, is that many studies are far too small to answer the questions posed with any degree of accuracy. But nevertheless, they're very useful in that they might give us an idea on what research to do next. So the sample size will also affect the p-value and the confidence interval, and which they tend to actually be smaller in larger studies. Let's have an illustration on how these might be affected. Suppose we carry out a study comparing a treatment in two groups and test for a significant difference in whatever outcome we are measuring. Initially, we will have limited funds. We can only afford to have 10 participants, whether people or animals or cells, etc., in each group. We find that 2 participants have the outcome in the first group and 3 participants in the second group. So we have a 10% difference between the two. However, the p-value is nearly equal to 1, which is very definitely not significant, and there's no evidence at all to suggest that the difference exists here. So we go back to the funding body and ask for more money. Now we can afford to recruit 100 participants to each group. Again, we observe the same kind of percentages. 20% experience the outcome in group 1 and 30% in group 2. Hence we have the same difference of 10%, but our p-value, however, has shot down to 0.1. It's still not significant, but is certainly considerably different than with the previous smaller sample. Convinced that our treatment is effective, we get funding for an even larger trial, this time with 300 participants in each arm. Again, we have exactly the same observed difference of 10% as last time, and this time our result is highly significant. Well, the treatment works for sure, although we are still seeing the same effect difference as we saw in the earlier trials. You see that the difference is exactly the same, but the difference in the sample size has made all the difference in the significant levels. The point I'm trying to make here is that a p-value isn't really an arbitrary and meaningless value in the absence of a sample size calculation. Without it, how can we be convinced that the sample size is large enough to have the power to detect an effect if an effect exists? Having said this, we need to remember that in basic science we are usually looking at differences much larger than 10%. So we need to bear in mind that the p-values will be affected by a different scale. This is just for an illustration on the sample size. Looking at the sample size related terminology and components, just for information, we will need to have available the effect size. This is the biologically meaningful difference we want to detect. It really should be the minimum difference that is clinically important and one that potentially could change practice. In general, the larger the effect size, the greater the impact of an intervention or a difference between the two groups. We will also require an estimate of the anticipated standard deviation of the outcome we are interested in measuring. Together with this and the effect size, we are able to calculate the standardized effect size delta using that simple formula, and we will explain a little later on why this is useful. Then we have the type 1 error, which is the probability of rejecting the hypothesis when it is true. So it is really the incorrect acceptance of a hypothesis, or as otherwise is known as the false positive. Essentially, the type 1 error is reported as the well-known p-value, and we saw how it can be related to poor design or inappropriate population as well as random chance. Next, we have the type 2 error, which is the converse, if you like, is the false negative, and it is the incorrect acceptance of the null hypothesis. In other words, we're not rejecting the null when we should have done so. Or putting it another way, we're making a type 2 error when we fail to observe a difference when in truth there is one. We can make a type 2 error when, for instance, there are too few events for comparison between the two groups. Finally, the power, as mentioned earlier, is the chance a study has in detecting a difference between treatment arms, providing a difference exists. It's calculated as 1 minus beta, where beta is a type 2 error. There are mathematical formulas on how to calculate the sample size, so your scary option is to use them, but I realize this is probably not the preferred option for most people. Alternatively, there are a number of software options that they deal with the sample size and power calculations. Some are free, some are paid. I actually feel it is beyond the scope of this presentation to show a preference to one as opposed to another. What I could do, though, is show you a nice and simple, quick way of calculating the sample size for certain situations with what is called the Altman nomogram. And here's what it looks like. The components we need here is, and we need to have them predetermined, is the standardized difference, the power, and the significant levels. The limitation of the nomogram is that it can only cope with a 5% and a 1% alpha, the two lines there. The upper limit being the 5% and the lower line being the 1%. So let's look at an example to see how that works in practice. The question is, how many patients in each group do we need in order to detect the standardized effectiveness of delta equals 1 with an 80% power and a 5% significance level, the significance level being the alpha. On the left-hand side and on the right-hand side, we have the standardized difference axis and the power axis. So if we locate those, we can then draw a line between them two, and depending on the alpha that we chose, in this case the 5%, we see where the line we draw cuts the sample size line, and that is the number of people that we need. In this case, using the nomogram, we found that we need 30 people. In other words, 15 per group. It's a very nice and easy way. It only deals with 2 levels of alpha, and it is unfortunately you're not able to use it in all situations, but hopefully for most of what you need will be a very useful little calculator to have at hand. You can find it in this book, in Practical Statistics for Medical Research. So next consideration in the design stage should be randomization. Randomization is really the random allocation of subjects in each groups, and it's quite important because it protects against a number of biases. Blinding, in other words, hiding who got what and at times who is analyzing what, should be an integral part of randomization. Really, blinding and randomization are very important issues that merit a very long lecture in themselves. So we're not going to cover them completely here, and my suggestion is not to rely on these couple of bullet points, but explore the subject rather well before trying to employ it in your study. Moving on to the data collection considerations and aspects, let's have a look what we need to think here. It's quite important to decide on the correct items to collect when you're doing your data collection. Try to collect items that are useful. For instance, if we were looking at, let's bring an example here, at the effects of malaria medication, it would be rather important to know where the experiment takes place, because in sub-Saharan Africa, that is more important than perhaps any effects noticed in Northern European countries. The next thing will be to check the collected data. It's very, very important to know your data, know your data well. And one way to do that would be to summarizing using tables or graphs before starting any further analysis. Innocuous typos may alter the results. At this stage could be just little typos and very inconsequential. But let's say that garbage into an analysis at this stage gives garbage out. So describing and summarizing your data before any analysis is a rather crucial step. Once we know we have the correct data, we can explore the normality of the data and why this is important. This is an important step because it will help us to find out what analysis we can do. There are different tests to explore normality, and depending on whether the data is normally distributed or not, there are different statistical techniques to choose from, and we're going to explore them shortly. So let's see how a data looks when it's normally distributed. This is the well-known bell curve, and you will find that the mean, the median and the mode, if you're exploring a continuous variable, should all fall more or less at the same point. If your data is not normally distributed, then those measurements, the mean, the median and the mode, will not all be the same. In this case, we will have a skewed distribution. When we have a normal distribution, we have normality. We use parametric tests. When we have a skewed distribution, the non-parametric tests are more appropriate. The next stage will be, if we have non-parametric tests, to decide whether we need to transform our data or not. Some experienced researchers will, or statisticians, let's just say, can decide on this by just looking at the data. But those who don't have a lot of experience, it might be helpful to have a test to decide on whether to transform or not. A data transformation will bring data back into normality, and therefore we may have a bigger variety of analytical tests to choose from. So we are now out of the danger zone. We have completed, if you like, the design steps of a study, and we're moving on to the analytical part. Let's have a look at considerations for the analysis. This is where we choose the statistical tests. And essentially, we just need to decide what test to do when. Here's a table that will help you choose, depending on what kind of design you have and what kind of data you have. And I'm just going to highlight the tests that you're more likely to use. You'll see that the left column shows you the options for when you have a normal distribution of your data, so that will be the parametric testing, where the middle column is when you have not normally distributed data, so you have non-parametric tests. The last column is a bit of a specialized column, and you can go to it when you have binomial data, in other words, when you have two states. The study that you have, the design that you have, very much will dictate what kind of statistical analysis you can use. So looking at them separately, if we have one group to compare to a hypothetical value, then you will be looking on the first row. That's the well-known t-test, or the Wilcoxon test if we have non-parametric data. If you have two independent groups, we have unpaired t-tests for the normally distributed data, where in basic research you're very likely to have matched groups. Usually those will come about if you have the same cell that is divided many times, and then you can use the pair t-test. If you have more than two groups, one-way ANOVA would be a good alternative. And if you have three or more matched groups, the repeated measures ANOVA. To quantify an association between two variables, I'm sure you all know the Pearson correlation and the Spearman correlation, respectively. Multiple testing, as it is known, is a serious problem that occurs much more often than we like. And we need to be aware how this might affect our results, as it causes actually type 1 errors. The essence of the problem is that if you beat the data long enough, it will confess. In other words, if, for example, we do 100 comparisons on the same data set, 5 could be significant just by chance alone. Put simply, the probability of identifying at least one significant result due to chance increases as more hypotheses are tested. We need to test for occurrences like that, and to do this we use what we call the Bonferroni correction. To perform a Bonferroni correction, we need to divide the critical p-value, or the alpha we have chosen, by the number of comparisons we do. So for example, if our chosen alpha is 0.05 and we have 10 hypotheses being tested in the same data set, the new critical p-value would be considered as alpha, 0.05, divided by 10. The statistical power of the study, like we talked before, should now be calculated based on this modified p-value. The Bonferroni correction is rather crucial and is used to reduce the chances of obtaining false positive results when multiple pairwise tests are performed on the single and the same data set. Finally, we have come to the interpretation stage. The considerations we need to think about here is really to discuss whether the findings are biologically relevant, first of all. We have a go to answer the question, so what? So what if the numerical values look all very significant? Does it actually make a difference in our policy, in our treatment of patients, in our further research, in anything at all, in fact? If we have gone down pathway analysis in our basic research, perhaps we'd like to consider principal components analysis at this stage. Once we have crossed a few loops between analysis and interpretation, we're probably ready to write up a draft for the publication. At this stage, we need to decide on how to present the data. It might be useful, some of the explorations we did earlier, to be included here, like box plots or error bars. Certainly report medians and means and standard errors if necessary. Crucially, we need to have p-values and confidence intervals together when we are writing up the results, because as we said earlier, these are complementary. And the information that each one gives helps us to decide how important is the effect that we observed. And during the discussion, and the critical, and the critique of our results, it's very important not to inflate what we have found. And one thing to remember here is that there is no such thing as a tendency or a trend towards significance. It's just best to put our results as we have found them without trying to create different impressions. Finally, it's quite important to choose a relevant journal with an audience that will be interested in the research that we do. Good luck!